In this video, we're talking addition rule and mutually exclusive. The first, addition rule, is a tool. It's a formula that we can use to tackle bigger situation. Mutually exclusive is a definition, something that we can use to identify the relationship that outcomes or events have with each other. Let's talk about our first example. Much of our introduction here is going to center around this idea that we have a local university, 32% of which are freshmen and 4% are math majors. And so I have my little Venn diagram up top here showing, again, maybe there's overlap, we're not quite sure, but let's discuss what that interaction is. And there's two different relationships that we can look at here. The first is freshman or math major, and the second one is freshman and math major. Let's talk about the or one first. So we're going to define, whenever we read or, E or F, we call it a union. It's our fancy word for it. We also have a fancy symbol for it as well, that instead of seeing the or, oftentimes we can see a U instead to denote the same exact event. In fact, if you want to see what that looks like, U, this is what it looks like. E, and it's right, or union F is another way to read this. Now look, union is the most friendly one, right? Little smiley face, because it's really anything goes. If E is satisfied, we're good. If F is satisfied, we're good. If both, this is like anything and everything goes here. Very happy, friendly union. The second one's a bit more strict. If you read and down over here, E and F, a bit more strict. This is denoted as an intersection. If a shorthand for writing and is, we often see this N symbol, again, standing for intersection, E intersect F, or E and F. This one's much more strict because it's satisfied only if both of these are satisfied. So a bit more strict, a bit more difficult to evaluate. There's a little trick that I want to get implanted in your mind right now, and I have it written just beneath me. And anytime you read E or F, you should think, I know what I'm going to do. I'm going to add these two. There's a little formula to work around that, but that's a good association to make, that you read or, you think add, and then a little bit later, when you read and, you should think multiply. E and F, think multiply. And this is a good way to associate formulas with these terminologies. And so again, the formal, union, intersection, but the less formal, think add and multiply. Let's get into it. Let me slide over here. That's a little better. Consider at this local university, again, I have my Venn diagram over here, 32% freshmen, 4% math majors, and maybe there's an overlap, we're not quite sure. Now notice if I'm closing my eyes and picking a student at random, we can talk about the probability of getting a freshman, 0.32. We can talk about the probability of collecting a math major, 0.04, 4%. What if I'm interested in the union, or anything goes? Well, as the rule of thumb that we like to think of, anytime you read or, we shouldn't think add. And this is why this naturally occurs, that if I'm looking at picking either one, freshman or math major, that would be 0.32 plus 0.04. And that may get you close to the answer, but not quite. And here's why. If I look at those freshmen, I can write horizontal lines on those individuals. This is me like counting them up, if you will. And then for the math majors, let me change colors. And if I calculate those math majors, we'll do pretty close to vertical lines. And I can add them up here. One thing to notice that we should be concerned about, if I was adding these two spheres or these circles up, is I counted this inside, this middle area, calculated it twice. First, when I was adding up those freshmen, and then second, when I have those math majors, twice. Not good. So when I look at my freshmen and math majors, that overlap, what is it? If I quantified it, say maybe I said that quantifying that intersection was 1%, 0.01, well then maybe now I can figure out, if I counted it twice, maybe there's a way I can take out that second path. In fact, that little idea is exactly where we get addition rule. You can start twice. This one's a very important one. It looks like this, that if you have two events, then the probability of their union, probability of E or F, and we see or, we think add, I can do them separately, is the probability of E on its own plus the probability of F on its own, and then minus that overlap, E and F, take out. And again, the whole reason I want to take out or minus that overlap is because when I do E and F, I counted that overlap twice. And so to take out that extra one, we remove it. And that's exactly what that addition rule is all about. Let's do some examples with this addition rule. Given the following information about events A, B, and C, I want to find the probability of A or B. Let me first start off just with writing the formula. I have the probability of A or B. Again, anytime you read the word or, I'd encourage you to write to yourself, okay, that means I want to add. And there's a nice little formula that we get from it. And the formula looks like this. I should write the probability of A on its own plus the probability of B on its own minus the overlap, the probability of A and B. Again, that's straight formula, no trickery yet. Now to actually evaluate the probability, well, we need to look up what is the probability of A. Now this is an event that's tied to something that we can evaluate that probability separately. Fortunately for us, they're giving us the probability of A. It's 0.4 or 40%. Plus the probability of B, we can view it over here, is 0.6 or 60% minus that overlap A and B. I can find it over here. Looks like 24% or 0.24. And so I can add and subtract these together and we should get 0.76. And that's our probability there. Again, if you want to think that as a percentage, I can write 76%. And so when they're asking us these events, I don't even need to know what A is, what B is. I can find these events using some algebra, adding those events up independently and then subtracting that overlap. And so this is the beauty of this addition rule formula. Let's see if we can get an example more concreted in a situation. Suppose that after a vote in the U.S. Senate on a proposed spending bill, the following table shows the breakdown of the votes by party. I'm in the way a bit, but you can see there's Democrat, there's Republican, there's Independent, and then above voted in favor or voted against. So let's say a lobbyist randomly stops a random senator after the vote. What is the probability that this senator will either be Republican or voted against the bill? And so, or we're looking for a union between these two. Let me slide over here. So I want to first start off by defining the event we're interested in, and I'll do some shorthand. Probability of Republican, I'll write an R for that, or against the bill. So I'll write an A for these two. Again, as we're getting started, I encourage you read or write add. Note to self, there's a formula for that. And so I'll write this as the probability of R plus probability of A minus the overlap, probability of R and A. As a side note, there is a way that you can do this without the formula, but I want to show you why we need the formula. That's why I'll start off with it. And so I'm looking for Republican or A. First, let me talk about these Republicans. I can look at them over here. It looks like I have 18 plus 24 of those individuals. In fact, I know the total is 42 there. Those are my Republicans. If I want to also talk about Republican or voted against the bill, well, that's going to be these individuals over here. And so if you want to look at this like a Venn diagram, I have my Republicans, I have my against. There is some overlap over there. In fact, I can tell you what that overlap is. It's 24 individuals. And so each of these parts, these probabilities, if you wanted to find them separately, you could. You could also find them together. But let me show you using the formula. For Republicans, again, they're my little circle there, 18 plus 24. There are 42 of those individuals divided by the total, which is 100. Again, to recall, probability always number that we want up top divided by our space down below, plus those people who voted against. Very coincidentally, 7 plus 24 plus 11 is also 42. So I'll write for against 42 divided by 100, and then minus what is that overlap? That's these individuals over here, these 24 people. So I should write this as 24 divided by 100. Here we go. Equals 42 divided by 100, very fancy, is just 0.42, plus 42 divided by 100 is 0.42 again, minus 24 divided by 100 is 0.24. If we added and then subtracted, again, that's 0.42 plus 0.42 is 84 or 0.84. I can subtract then, and I should get 0.6, or as a percentage, that's 60%. And so what's the probability that a lobbyist stumbling through randomly bumps into a Republican or somebody who voted against? Well, I mean, it's greater than 50%, 60% chance, or 0.6 as a decimal. Again, you can use the formula. You can also avoid using the formula as well, but I want to stress the formula for this example. In a particular statistics course, we have 87% of students pass the first exam, while 72% pass the second exam. So we have 2 exams and we have their pass rate. If we want to look at the combination, 65% passed both exams. What I want to do is I want to find the percentage of students that passed at least one exam. Let's start off here. Let me slide over here, a bit more space. There we go. Let me start off first with writing what this means. So I'll write it over here. Probability of, they said, at least one exam. It's important when we're reading these probabilities that we understand the situation that we're going into. Notice it says at least one exam. That means they passed the first exam or they passed the second exam. And they could have even passed both of them. It's like anything goes. So when we read at least one exam, again, I can think of all the different passings. It's like no exams, 1 exam, and 2 exams. Or passing. I want these two. That is, they passed the first one or the second one. Okay, I think we figured out how we're going to work this thing. This is the same exact event as the probability that we pass the first or second exam. At least one exam is the same thing as they pass 1 or 2. And again, the second you see or, you should think add. And this is how we're going to translate into the formula. Second you see or, you should think add. So this is the probability that they pass the first exam, which I'll denote with a 1, plus the probability that they pass the second exam, which I'll denote with a 2, minus their overlap, the probability of 1, big old and 2. Now we have each of these. And so now we have to figure out what is the probability that somebody passed the first exam. Well, there it is. It's exactly written out, 87%. Let me convert that to a decimal. Move this decimal over 1, 2. And I should write this as 0.87 for my probability that they passed the first exam. Plus, for the second exam, 72% passed. And so it's going to represent 0.72 minus their overlap. That is that they passed both of them. These are the great students that did well on both of those tests, passed them both 65% or 0.65. If you want to add and subtract those, you should get a pretty high number. It looks like 0.94. It's like, come on, they did something. They passed the first one. They might have passed the second one. They might have passed both. Anything goes here, right? These are the students that are doing something. Second, find the percentage of students that passed neither exam. I'd encourage you always start off with trying to figure out what this event is really representing. So I'll write that they passed neither exam. Sometimes it helps to bring up a table, which is exactly what this above is. Little table about all the outcomes that are possible. They passed neither exam, no exams, 1 exam, or 2 exams. This is everything in the whole wide world that can happen. Well, neither exam would reference that they passed 0 exams. And so let me write this as the probability that they passed no exam, or 0. 0 exam. Interesting enough, we had this formula way back in the day. Let me see if I can write it maybe a different color so we can reference it here in a minute. But whenever we're interested in finding an event, for instance, 0 exams, this is what I want. I'll call that A. That's what I want. Well, then what I don't want over here, A complement, the opposite. These two have a relationship. The relationship looks like this, that the probability of A occurring is equal to 1 minus the probability that A does not occur. And so this is a nice formula for complements that we can use. That's what this C stands for, complement, opposite. And so if I want to find the probability that they pass no exams, I can do so. There's a nice little trick workaround that I can do. If I want no exams, that's my A, if you will, then I can find the complement, and that'll evaluate to my probability, provided that I take 1 minus that. I can write this as 1 minus the probability that they passed no exams, complement. But we know what that means. The opposite of them passing no exams is the probability, 1 minus the probability that they pass at least 1 exam. At least 1 exam. These are the complements of each other. Again, the opposite of doing nothing, no exams, is doing something, at least 1. But we know what the probability that they pass at least 1 exam. In fact, that's what we did in part A. So this is just 1 minus the probability that pass at least 1 exam is 0.94. So final answer should be 0.06. It specifically says to write our answer as a percentage, and so we can do that. This will be, if I take that decimal, 1, 2, I can write it as 6%. And you know what? We should do our due diligence and fix up here. For 0.94, this should represent 94% to write our answer as a percentage. And so whenever you read these events, they might be phrased differently, at least one. Try to understand in terms of what the question is asking. A nice way to do that is to write out a little table, a little sample space, everything that's possible. And sometimes those sample spaces can help alleviate or get an answer out of it. This is the most classic example out there working with Venn diagrams. Let's get into it. Find the following probabilities. Consider the Venn diagram where. So we have these two events. I have event A and event B, and all of these events are defined in this big space. That's what this S stands for space. Now, each of these events, event 1, 2, 3, 4, and 5, they have their own probabilities given. So for instance, the probability that event 1 occurs, it's right here, is 17% or 0.17. But I want to look at a collection, specifically these collections. Find the probability that B occurs, right, equals. Again, if you print off notes, if you have them, I'd encourage you to write. The interaction will be a lot more meaningful than simply passively watching. So interacting, making your own notes, going to prove beneficial. So I want to find the probability of B. I can circle it right over here. This is what I'm interested in, everything inside of B. And so I'm drawing my little circle to denote, hey, this is B. Well, there's two events inside of B that define. So I'll write here, the probability of B is equal to the probability of E2 is inside of B plus the probability of E3, that these two events are inside of there. Well, both of these probabilities I can pull from the table above. The probability of E2 is 0.08 or 8%, plus the probability of E3 is 0.2 or 20%. If I add those together, I should get a 0.28. And there's my probability that B occurs. And so it's understanding what the events do, and then we simply pull and add probability. Let's look at another example. Probability of A stands for complement. Or you can think about it as the opposite or outside of A. This is going to be equal to. Again, it always helps sometimes to draw a picture. If this is A, this is A inside this circle, well then A complement is everything on the outside. In this case, I can just circle. There it is. This is A complement, everything on the outside of A. I'll write it here. Outside of A. This is going to be equal to, let me extend these equal signs here, the probability of E3, that's outside of A, plus the probability of E5, also outside of A. Both of these events I can pull from up top. That should be 0.2 for E3, plus for E5, that should be 0.36. I can add these two numbers together. That should be 0.56 or 56%. Let's look at some combinations, some intersections, and maybe some unions here. So let me see if I can combine these two together. A complement, or outside of A, and B. Again, and we're thinking, look, this is pretty strict because it has to be both A complement and B. As a side note, another way to write, instead of writing and, if you want to be a bit less expressive, you can use this intersection symbol here. Intersect. All right, this is what we're interested. Both of these two, A complement and B. Cross these off a bit. So from A complement that we had before, this E3 and E5, this was A complement. Let me change different colors here. Let's do green. I like it. Here, for my sphere, that's just a circle. Let's not be too fancy. This is B. And so if I want to find their intersection, what do they both have in common? Again, you might be tempted, E2, E3, E5, but that's in all of them. That's in some in B, some in A complement. The only thing that they have in common, is right over here, is E3. That's the only thing they have in common. And so what's in the intersection? It's just equal to the probability of E3, which we can look up top. Very popular response should be 0.2. And there's our probability, A complement and in B both. What about the union? Anything goes here. I have the probability of A or B. All right, not quite A complement, but A. Fair enough. So or. Whenever you think of or, you can think of adding, meaning I can use that formula, probability of A plus B minus the intersection. But another way I can do this is I can simply write out what these events are. Again, anything goes. All right, anything here. Dude, if it's an A, great. If it's in B, even better. So let me draw a picture here. Erase my work from before. Draw a picture. So again, I had A. That one's nice. Everything inside of here. Or everything inside of B, and all of these are fine. And so I'll write them together. And anything goes. If I want to find this probability, there's actually two ways to do it. Let me demonstrate the long way first, but we won't do it this way. As I can do this by looking at all these events, this would be the probability of, I could do E1 plus the probability of E4 plus the probability of E2. That's what they have both in common, and then plus the probability of E3. And you could add all these up. We could write all the probabilities, but this might take a little much. Let me also denote, mostly for posterity's sake here, that this is what's in strictly in A, and over here, this is strictly in B. And then of course that E2 is what they have in common. But there's actually a more efficient way to do this instead of adding up these four numbers. Let me look at the chart. Let me write this. This is what I want up top. Everything that I want. And so over here, this is like what I want complement. And so there's actually a faster way. Instead of adding up those four events, I can simply, if we understand complements, I can take 1 minus the probability of E5. And I'll write for reference sake that this is what I want, complement. And so I can simply remove what I don't want here. And so the probability then, again, a little bit easier to calculate. We do so down here. It should be 1 minus E5. That's 0.36. So as a probability, that should be equals to 0.64 or 64%, which would be the exact same thing you'd get if you added up those four probabilities. Exact same answer. One is just a little bit more long-winded than the other. There are many ways to evaluate probability here. I want to introduce the term mutually exclusive, but I want to do so through an example. This card example is a classic. It's a staple. A single card is drawn from a standard deck of 52 cards. The following letters are defined as events as follows, and we're going to evaluate some probability using it. So just as a little example, whenever you see the character R in an event, it's just going to refer to a red card, in which case I can see there are 13 hearts over here. There are 13 diamonds. And so altogether for the reds, there are 26 of those cards. And so on. B is for black, A is for ace. I can count up the aces. Here they are. There are 4 aces to speak of. So just getting comfortable with dealing with a deck of cards. Again, you have your suits, spades, hearts, clubs, and diamonds. And you have your different characters as well. Ace, 2, 3, so on and so forth. Then your jacks, your queens, and your kings. So let's deal with some events, and then we can actually pull some probability here. The first one is just the probability that, and think about closing your eyes and picking out a red card. We can do this. Again, whenever you're doing probability, we can always start with the basic. And then as we have a fraction, and we're interested in the number that we want up top, divided by how big our space is down below. And so the number that we want, a red card, well, we just talked about, there are 26 of those cards, 13 hearts and 13 diamonds. Out of the total, how big is my space? You could count them up, or you could have 13 plus 13 plus 13 plus 13, or check it out, they gave it to us right here. There's my space. There are 52 cards in total. If you divide those two as a fraction, that would just be a half, because half the cards are red. So my probability is going to be 0.5 or 50%. What about this next one? The probability that we grab, A stands just for ace. For aces, well, again, number that I want up top, there are 4 aces out of the total 52, or there is 1 ace for every 13 cards, because there's 1 per suit. And so this probability is going to be 0.08. And I can have my probability there. Not super likely, but certainly it's on the board. Let's look at some more complicated interactions between these different events. So now I want to find the probability of getting a black card or an ace. Black card or an ace. Again, or is very friendly. So we can think of anything goes here. And again, whenever you read the word and, you should, or I'm sorry, you should think of add. But we can actually do so inside of the fraction. Let me show you what I mean. So we can write up top, again, always number that we want up top, divided by how big our space is, equals. So let me write it like this. And again, up top, I'll think add. Let me show you what I mean. So the space is very friendly. There's 52 cards to choose from. The space is not going to change. But what I am interested in is first looking at my black cards, and I can see there are 13 spades, there are 13 clubs, and so there are 26 black cards to choose from. Plus, this is where the trick comes in. If I'm interested in my aces, I can see there are 1, 2, 3, 4 of those from the 4 groups. But some of you might be like, oh, mistake, don't write a 4 there. That's okay, let's fix that. Because we can look at this as the probability of B plus the probability of A minus the overlap, which is -2. All right, black and ace, which is why, again, you could have 4 minus 2, or you could simply just write 2 altogether. So when I work my numerator up, how many cards are there for what I want? I could write that as 26 plus 4 minus 2 is equal to 28 divided by 52. As a decimal, I should get that as 0.54, a little bit over 50%, because I have those 2 extra red aces, 0.54%, or anything goes. So let me look at what that overlap is. What if I'm just interested in the overlap? That is, I want a black card, and it has to be an ace. Again, aces are and is very particular. It has to be both. And so I can write this as a fraction. Well, there's only 2 cards that satisfy that, and it's the spade and club ace. And so I'll write this as 2 divided by 52. As a decimal, that's 0.04. Don't count on it. Don't count on it. 0.04 is my probability there, which again comes out from the formula that when you read or, you think add, take out the overlap. And that's exactly what the overlap is. And so we see that reflected here. What about a red or a club? Probability that we get a red card or a club. This one's quite interesting. Let me show you. Again, or very friendly, anything goes. And I can think about this as adding. Again, 52 in the denominator, that's my space. For red cards, well, there are the hearts and the diamonds. So I'll write over here as a reference R. There are 26 of those. Plus, for clubs, well, that's right here. These are these 13. This is what the clubs look like. There are 13 of those. And then we need to think, okay, is there any overlap? Well, not really, because I'm talking about this 3/4 of the deck, red or a club. So I can write that then as 39 divided by 52, or as a reduced fraction, you could write that as 3/4. Not that you need it, but you can write it there. As a decimal, it's going to be 0.75. So when somebody asks, hey, what's the likelihood that you get a red or a club? You're like, super likely, 75%, or maybe fairly likely. That's a good probability, good chance. What about, so that's or, union. What about the intersection? That's red and a club. Again, and very strict. They has to be both. Equals, well, again, you can write always up top how many cards are doing what you want them to do, divided by your space. Here we go. Well, the space always stays the same. That's 52. That's all the cards that I have to pull from. Number that I want. If I look up top, red cards, I have the hearts and the diamonds, clubs. What's the overlap here? Trick question, kind of. There's no red and club. It's impossible. In fact, that's what bore out over here, that I didn't have to minus anything at all, right? 26 plus 13, I had no overlap. I had nothing to subtract or take out. So go figure, I have nothing to count for red and club. And so what's the probability? It is exactly impossible. It's 0. Impossible. Never going to happen. And so we have a special name for this situation. Impossible is a good one. Probability 0 is another one. Another nice term to talk about when 2 things cannot occur simultaneously. Here's our term, mutually exclusive. Nice little term that we have. What's important to understand is when we talk about mutually exclusive, we just mean an event or 2 different outcomes that cannot happen simultaneously. And that's the example that we talked about before when we mentioned a red card and a club. Red and club. Those two are mutually exclusive. They cannot happen simultaneously or together is another word to think about it. Again, if you could imagine, if I had a deck or I had a hand of 2 cards, I could certainly pick up a red card and I could pick up a club, but those aren't simultaneously. Those are sequential. So it's very important that we understand the difference of things happen simultaneously versus things happening sequentially. So one of the friendly things we get when we talk about mutually exclusive, meaning that there's no intersection, well, normally the addition rule says the probability of E or F, again, or think add, that I have E on its own plus F minus the overlap, probability of E and F. But look, if there's no overlap, there's no need to write it. A nice little example of 2 mutually exclusive things is if a student's applying for a tuition cost, there's no overlap between in-state tuition and out-of-state tuition. It is, those 2 events are mutually exclusive. They cannot happen simultaneously, especially not for one specific student. And so that's my little example. Here's the little formula that you get from that. Again, mutually exclusive means there's no overlap. The probability is equal to 0. It's impossible. So for our last example, we're going to look at some situations and see if the pairing is mutually exclusive or not. For these examples, you can refer back to the card display that we showed earlier. Here's our example. A single card is drawn from a standard deck of 52 cards. The following letters are defined as the events. Again, like we talked about before, here's my red cards and my black cards. We can get more creative and talk about H for heart card. There are 13 of those hearts. Let's get into it. Determine whether the following events are mutually exclusive, which again is the same thing as saying they cannot happen together or simultaneously is another way to talk about it. They cannot happen together. And so I'm interested, when I pick up a card, can that one card be a heart and a spade at the same time? Heart or a spade? I'm going to look at that. Can those both happen simultaneously? Heart and a spade. Not quite. Those are different events altogether. So whether they're mutually exclusive, they cannot happen together. And so the phrasing is quite strange. That's why I'm trying to be precise. They cannot happen together. So are they mutually exclusive? Yes. Mutually exclusive. They cannot happen together. Let's look at the next example. Determine whether the following events are mutually exclusive. I want a red card or an ace. Again, can both of these things happen together? Can I look at a card and that card is both red and an ace? Well, yeah, it can. In fact, there are 2 red aces. 2 red aces. All right, here, real big, can happen. Therefore, it is not mutually exclusive. And so then it's a beneficial exercise to maybe come up with any old pairing that you can imagine. And again, there's a lot of examples that could exist here. List a pair of events that are mutually exclusive, and everyone should get the same answer for this one. Find the probability that they occur simultaneously. This is a goofy question. The first part is what pair of events exist here. A nice one would be maybe club and any other suit. Let me do diamond. Diamond. All right, these 2 events are completely mutually exclusive. I can't look at a card and it is both a club and a diamond. Or maybe you want to be more creative. You could say, I can't look at a card and it be an ace and a king. That cannot happen together. There are a lot of different pairings, but we should all get the same answer here. What is the probability of getting a club and a diamond? Well, again, no matter what your pairing is, the probability should be the same because by definition, mutually exclusive, the probability is always going to be 0. And so that's how we can turn that definition into a friendly response. And so let me bring it all together here. We've talked quite a bit about these different tools, this addition rule formula that we can use. And right now we kind of really only have 2 tools in our arsenal. The first one is complements, that sometimes looking at it is difficult. We can look at the opposite instead. Nice formula with that one. And the second tool now we have is this addition rule, that anytime you see or, you should think add. I can look at each individual probability separately and add those up. And then of course we have some terms like mutually exclusive, meaning look, these things cannot happen together, important to differentiate between. Let me close with this. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.